Hey everybody, you know your teacher's a real nerd when there's whiteboard in her house. So here we go. These are my hints to help you get started for any of your work relating to the falling yo-yo part of the problem. I'll do the rolling yo-yo in a separate video. So here we go, right? Let's think about what's happening first. So this is our falling yo-yo. That's spelled correctly. So our falling yo-yo, what's happening, right? We've got our yo-yo, and we've got the force of gravity acting down on our yo-yo. And there's a string, right, that's providing the torque that's making our yo-yo rotate. So we've got a force of tension acting up, and we've got the force of gravity acting down. Those are the only two forces acting on our yo-yo. So here's a couple things that we know. First, because that string is on the outside of the inner cylinder of the yo-yo, it's going to cause the yo-yo to rotate. There's a distance between the point around which our yo-yo is rotating and where the force is being applied. So that means we know that there's going to be a torque. And a torque is a force times that distance, and we use r for radius, right? From the distance from where that point of rotation is to where the force is applied, the sine of the angle between those two. So that's one of the things that we know. We also know that a torque is equal to our moment of inertia times our angular acceleration. Right? That's the rotational equivalent of Newton's second law. So this equation right here is equal to this equation right here. So that's how we're going to bring all of this together, because as we're solving this problem, I is the thing we want to find, right? We want to get a number for I. So everything else that's here has to be something that we can figure out and measure. So we're going to need to figure out what is the force that's causing that torque. We're going to need to figure out what is the angular acceleration of our yo-yo. We're going to need to figure out what's that distance between the center, the point of rotation, and where the force is applied, and what's that angle. If we can get all of those other numbers, then we can just do algebra and figure out what I is. So let's take these sort of one by one. Um, I'll make my little list here of what my known and unknown values are so that we can figure it out. So there's a couple things that are known, right? We know what that R, that radius is. That's the radius, that's the inner radius of our yo-yo, and that's given in your problem. And it's 0. What is it? 0.005 millimeters. 0.005. We know that the theta we're talking about here is the angle between the radius of our rotating object and the vector direction of the applied force that's causing the torque. So that's a 90-degree angle right there. So that also tells us that sine of 90 degrees equals 1. So that's going to help us out. And everything else, the force and the acceleration, we're going to have to figure those out based on some of the other measurements we've got. So you know that the mass of our object is 0.014 kilograms. We also know that somewhere in here, this is a falling object. So we've got the acceleration of gravity, 9.8 meters per second squared. And let's go ahead and make a decision right now. Because our object is falling down, I'm going to call down the positive direction and up the negative direction. So the only thing that we need is we need to take all this known information, our experimental data from the video, and figure out what alpha, what our angular acceleration is, and what that force is right there. So let's think about that angular acceleration first, right? One of the other equations you know is that a linear acceleration is equal to a radius times an angular acceleration. So a little bit of algebra tells me that that fishy thing, angular acceleration, is equal to a linear acceleration divided by the radius of the object rotating. So now I know that this R, I've got that number taken care of. So A right here, that's something that we're going to figure out from our experiment, right? So this little a needs to be something that we look at from the data. Now, I saw a lot of people so far as that's illegible. I've seen a lot of people so far as we've talked through online, or people have emailed me. I've seen a lot of creative equations for acceleration that people use. Acceleration is not just a distance divided by a time squared, right? So the best way to find your acceleration is going to be to graph your data using a spreadsheet. On your x-axis should be time in seconds, and on your y-axis should be your change in position, your displacement, or your distance in meters or inches, right? Inches is what I had on my ruler, so you can choose to either convert those first or to convert those afterwards. But you should, when you plot your data, get a curve that is increasing as a polynomial, okay? So you're going to actually find the best fit line for that data on your spreadsheet, set your equation, your best fit line to polynomial, and then you'll also want to say you want to label it with using the equation. You can find that equation. It's going to give it to you in a format that looks like what you may have seen earlier in the year when we did this a few times. You'll get an equation like this. They'll give you a constant value plus a constant times x plus a third constant times x squared. I call these C, B, and A because we usually look at quadratic equations the other way, right? With our x squared term being the first term. This term right there, that coefficient matches up with our equation for displacement, where you can take this coefficient right here, and it's equal to 1/2 times the A that means acceleration. So if you take this coefficient A times 2, it will tell you the acceleration graph. So that's how you're going to figure out your acceleration A. The other way you could do it is to think about acceleration is a change in velocity over a change in time. To do that correctly, though, you'll need to take each consecutive piece of data and find the velocity between those two, and then find the velocity between those two, and then find the velocity between those two, and the velocity between those two, and so on. So you see an increasing velocity, and then you can either graph those, and you should get a linear slope, or you can then do a third round of calculations, and you can determine how much the difference is between the velocities of those two, and the velocities of the next two, and the velocities of the next two. And more accurate. Do this. So that's how you're going to find your acceleration, right? And that's going to give you a number that you're going to get from your data. So now let's go back and think about this force, okay? What's this force up here? Well, here it's going to be whatever force is causing the yo-yo to rotate. Well, the yo-yo is rotating because gravity's pulling on it, and there's a string that's creating some tension to resist that. So it's actually a combination of those two things, right? They're making the yo-yo roll down. So let's think about what's the net force. We're just going to use Newton's second law like we're used to. The net force in this situation is going to be our force of gravity minus the force of tension. And that force of tension, that's what is causing our torque to happen. So we're going to solve for F of t right here. So net force is always equal to a mass times an acceleration. Your data. The force of gravity is always equal to a mass times the acceleration of gravity minus force of tension. So a little bit of algebra tells you that you've got the mass times the acceleration of gravity times mass times the acceleration you found up here. And that's the force of tension. So now, when we want to find what's our torque is going to be this force times the radius of our center part of our yo-yo, our inner radius, times the sine of theta, which we already figured out over here, is 1. So you now have an equation for torque where you know every single number. The mass is given. The acceleration of gravity, your favorite number. The mass is given. The acceleration you figured out from your data. And the radius, and again, that's the inner radius of the yo-yo, is something that was given and measured in your problem. So, the final step of this situation here, we know all of these numbers. So I'm going to set our two torque equations equal to each other. Mass times gravity, acceleration, like this. Our inner equals our moment of inertia, or our rotational inertia, synonyms. And then instead of writing in alpha, I'm going to put in acceleration divided by radius. So you can follow your notes for this algebra, because at this point, every single number is something we know, except for I. And your goal is to solve for I. If going through this algebra, if you're like, are you kidding me? I'm not in the classroom, you can't make me. You absolutely can plug in numbers earlier in this process. So that at the end here, you're just calculating things. You've got a number for this part, and you're saying a number equals I times A. You can absolutely do that, okay? But this is how you set up the problem for the first part, where you're trying to figure out what's the moment of inertia based on it falling down. Okay? Hope that helps everybody. All right.